Welcome back. This is our second in our two-part series on the citric acid cycle. And so if we come down here and take a look at our metabolic map, we're still looking at this citric acid cycle right here. In this video, we're going to focus on the regulation of that cycle. So kind of a review. Here was our citric acid cycle in lots of detail. And remember that the main catabolic function of this cycle is to produce high transfer potential electrons. So we see those in lots of spots here, right? And that ATP, sometimes GTP, depends on the cell. And then it also gives off carbon dioxide. So we make these high transfer potential electrons, ATP, carbon dioxide. Eventually, we're going to send this energy to the electron transport chain, and the electrons will be dumped off on oxygen. So interestingly, even though oxygen is not a reactant in the citric acid cycle, it's got to be present for the cycle to keep going, right? Because for the cycle to keep going, these electron carriers, right, have to be regenerated. And that happens in the electron transport chain, which does use the oxygen, and hence this is still considered an aerobic process. All right, down here we have the overall reaction shown. So you can see we use a lot of those carriers to generate lots of these high energy electrons to carry to the electron transport chain. We create that ATP and that waste carbon dioxide. All right, let's talk about the regulation of this cycle. When we look at this, we know that often the regulatory steps are those steps with a really high negative delta G value. It's hard for them to overcome that to go in reverse. So when I look at that, I'd be like, ooh, step 1 here and step 4. It looks like step 5, but notice we've got our kind of little two-part one. So when I look at that, that's what I would think. That steps 1 and 4 would be regulatory, but it turns out that it's not step 1 as much. What is really regulatory, or the big regulatory steps, are steps 3 and 4. So if we think about step 1, the real regulatory site in step 1 turns out to be the site associated with producing the acetyl-CoA. So we want to produce that acetyl-CoA, which is going to get used in step 1. And once it's produced, it really will just move into the cycle if that energy charge is low. So one thing is that it's just not once we have acetyl-CoA, this thing really does move forward. It's not likely to stop. But the other thing is that the acetyl-CoA is not committed to going into the citric acid cycle. So we know that our committed steps, where once we've done that step, everything else has to follow through the cycle, tend to be the regulatory steps. And if you remember, we talked about the fact that acetyl-CoA could also be used for say, make fatty acid synthesis. So anyway, steps 3 and 4 are really our key regulatory steps. Okay, because we know that in step 1, if our cell needs energy, our pyruvate dehydrogenation complex, that one from last time, will jump in and make the acetyl-CoA that we need. All right, so if we look at this way for citric acid cycle, okay, our pyruvate dehydrogenation complex, sometimes we also see that PDH for dehydrogenation, will jump in there. We remember that it was controlled with energy charge. So if we have lots of ATP, we've got lots of energy. It's going to slow down the formation of the acetyl-CoA. If we have lots of ADP, it's going to speed it up. And we looked at all that regulation last time. But once we're inside the citric acid cycle, we've got right here, this is our isocitrate dehydrogenase. So that step. And then right here, we have that alpha ketoglutarate dehydrogenation complex. And these are both heavily controlled by the energy charge. Okay, they're steps that we get lots of energy out, and it makes sense that they would be controlled by how much energy we need. So if we take a look, well, that's not where I wanted to go, I guess. Oh, I just wanted to highlight this. There we go. So when we already have lots of energy, we've already made lots of those high energy electrons, we've already got a bunch of ATP, okay, we're going to see those negatively affect these enzymes, allosterically affect as a negative inhibitor and slow this reaction down. Okay, on the other hand, if we see ADP, it'll speed up that first of those two. Okay. Come down here, let's look at this one. The succinyl-CoA serves as a negative inhibitor. That makes sense. If this is starting to build up, it must mean that our cycle's not continuing on, and it'll slow down that. So regulation here is really largely just ATP, ADP, the NADH. It's the energy steps. So a little easier than some of our past cycles. All right, here what I wanted to look at was the biosynthetic role. So we've been looking at the catabolic function, the energy forming function, but citric acid cycle also has an anabolic function. So these metabolites, these things that are made, are intermediates and important for other metabolic pathways. Okay, so for example, citrate can be used to make fatty acids, sterols. We already talked about acetyl-CoA, right? Can be formed, used in fatty acid synthesis. When we come down here to the alpha-ketoglutarate, okay, that's the starting material for some amino acids, some purines, so that can happen. Okay, we talked about the succinyl-CoA being a starting point for heme. Okay, and the oxaloacetate is starting material for our amino acid aspartate and then other things. Plus, we know it can go back up to make our glucose, right? So the concentrations of these metabolites will change, and when there's plenty of energy available, and we don't need this cycle to keep going to provide energy, these things will get pulled off to make these other needed items for our body. Okay, and then we've got to be able to replenish them when we do need energy. So when we're back at a low ATP situation, we've got to get that citrate and that alpha-ketoglutarate, oxaloacetate. All of these things need to be quickly replenished, right? So now we could make our acetyl-CoA from fatty acids if we needed to, or from the pyruvate. We can make that oxaloacetate from the pyruvate. So we can essentially call back these metabolites when we're at a low ATP and get this reaction going again. Okay, this down here is just an example, reminder of the reaction where pyruvate is forming the oxaloacetate. Okay, so then we would, when we're at low ATP, we need this energy cycle going, we would start making more of this. All right, let's look at a question. So acetyl-CoA is a activator. So this is really kind of a review question, but important because it pulls into our citric acid cycle. We can't have our citric acid cycle without this acetyl-CoA. So it asks, why is acetyl-CoA an especially appropriate activator for the pyruvate carboxylase? So if we come up here, our pyruvate carboxylase is this one that takes pyruvate to the oxaloacetate. On the way then to glucose is when we looked at it in gluconeogenesis. And as the acetyl-CoA right here increases in the cell, it means that this cycle has slowed down. right? If we're building this up, our citric acid cycle has slowed down, indicating that the energy needs of the cell are being met. And if that's the case, then it's safe to convert this pyruvate to the oxaloacetate, which then can be converted off to other molecules, up to glucose. We looked at amino acids, all these things it can be converted to. So the acetyl-CoA is essentially reporting on the energy needs of the cell. If it's piling up, we know that we can use the pyruvate for these other synthesis needs. All right, that is it for our second video on the citric acid cycle. Next up is the electron transport chain.